Unit 7-4, reference with Holt Chapter 5, Section 8, page 356 through 362. Okay, another special right triangle to remember is a 30, 60, 90. You will always be given on a formula chart the values of the sides opposite these angles, but it's good to know where it's been derived from. If you take an altitude of a equilateral triangle, notice that these have equal sides shown by these marks. If you break this into two triangles by forming an altitude, also known as the height of the triangle, and you form two right angles. This is your 90-degree angle. You've now bisected this 60-degree angle to make that 30. And this one we didn't bisect, and we know the equilateral triangles have all 60-degree sides. So 60, 60, 60 now becomes this 30, 60, 90 special right triangle. What we're going to be looking for is how they derived each of these values. Well, if you take the shortest leg and give it a value of x, and we know that what we've done is taken these two parts, and there's two of them, so this whole side, the hypotenuse, is going to be a value of 2 of my x's. The length of the altitude, which makes up the longest leg, I'll highlight it, can be derived from the Pythagorean theorem. So if you take the hypotenuse is equal to its 2 legs, and the longest leg being what we're looking for, you square everything, this becomes 2 times 2, which is 4, and x squared is x squared. You want to get rid of this, subtracting from both sides, and you'll be left with a 3x squared is equal to the longest leg squared. I showed in red that taking the square root of both sides gets the longest leg by itself. This becomes x square root of 3. So just a fancy way of showing how they derived the value of this highlighted long leg is an x square root of 3. Okay, so a lot of times you see this by itself, not inside of an equilateral triangle. So anytime you're asked to find the missing length of a 30, 60, 90, draw it. Draw an example and then just label the side lengths. And sometimes I try to teach kids with arrows. This angle measurement of a 30 degree measures this right here. It opens up to the opposite side, being a value always of an x. This angle, 60, that opens up the opposite side length from here to here, is always a value of x square root of 3, just derived from the Pythagorean theorem. And then always your hypotenuse is what's across from your right angle, and that value is always 2 of whatever this one is, with this value x. I tried to show this in 2 different scale models, one using the snap legs with red, blue, and purple, and another one, put it down here, with the orange, greens, and yellows. No matter the scale, what I'm trying to emphasize is that if you take an altitude and you break it up, 2 of these purples would make up the red. Same thing here. If you break up the altitude, taking this green line being the longest leg, 2 of these oranges make up the hypotenuse, which is shown in yellow. I could show that to you. Do it with this one. Is that 2 of these oranges make up 1 yellow, just as 2 of the purple, I'll unhinge it, make up the hypotenuse that's red. That's where that 2x comes from, because it takes 2 of these links to make 2 of this purple link to make up that. So always your value across from your 30-degree angle is an x, and across from your hypotenuse 90-degree angle is a 2x. You don't have to memorize this one. It's always given to you. The value of this length, the long leg length, is always a value of x square root of 3. So being able to draw that each time you can do these examples. Let's look at the first one. If we know the side opposite of 60 is always going to be a value of x square root of 3, and we know the opposite of my 30, it's not labeled, but we can label it. This is a 30-degree angle, is always a value of x, and then this value is equal to 2 of my x's. So if the value of Ln is 14, then Mn is going to be 7. We'll go ahead and label that, so we can know that this one's 7. So if this is, if x is equal to 7, this value from M to N, this whole distance from here is 7. If that's 7, then 7 square roots of 3 is what this value is going to be. 7 square roots of 3. You can also show it by solving for this, and that is 14. Well, we've already done this. 14 is equal to the 2x. Divide by 2 on both sides, and we get x is equal to, 14 is equal to 7. So this is a case where you're just taking that 7 and plugging it into the x. Not always doing that when you've been given the hypotenuse. So let's look at another example. We're going to be getting into our radical understanding of radicals. If you need to review simplifying radicals, do so with your teacher, because most of these answers are in simplified radical form, not decimal. Okay, again, labeling your sides. The opposite side from 60 is x square root of 3. This is equal to my x, and of course Ln is 2 of the x's. 2 of my purples making up my red. If it helps to remember the picture of the example, I think I'll put that over here. Knowing that 2 purples make up the red. You'll see it in colors. Look at that one like that right there. Okay, so if Ln is 2 x's is equal to 2 x's, then Ln is equal to 2 times 2 square roots of 5. When you're multiplying radicals, you can only take your whole numbers together. The other has to stay in radical form if it's under the radical. So let's label that 4 square roots of 5. And if Ln is 4 square roots of 5, then Lm is going to be equal, we know that it has to be x square roots of 3, and you've got 2 square root of 5 is my x, and you're multiplying that by square root of 3. All I did was I substituted the 2 square roots of 5 as my x, and then multiply it by 3. The only thing that can be multiplied here are what's under the radical, so this is 2 square roots of 15. Only multiplying these two together. Only the radicals. Okay, again, let's label our sides. X, this is equal to x square roots of 3, and this is 2x. So if Mn, let's do that one first, is 2x is Ln. Let's do that one first. Ln is equal to 2x. So 2 times our x is we haven't solved for x yet. We got to solve for x first. So if we need to solve for x, we're taking this right here. So we've got to do that one first. Let me move that over. Mn is equal to 8 divided by square root of 3. Because you're wanting to divide by both sides. If Mn is equal to, I should have put that there, x square root of 3. You're dividing by square root of 3 on both sides. So you've got 8 over square root of 3. Remember, we don't want a square root in the denominator, so you're going to multiply by a square root of 3. This is a product of 1, anything over itself, so I'm really just multiplying this by 1. This becomes 3, and this is 8 square roots of 3. So now that I have my Mn, 8 square root of 3 divided by 3. Leave it in radical form. Now we can multiply 2 of what my x is, because my Mn is now this. We're multiplying 8 square roots of 3 divided by 3. So 2 times 8 is 16. 16 square roots of 3 divided by 3. And that you have to leave like that. 16 square roots of 3 divided by 3. That is your answer. Should box these. Phew. Okay, one more. This one would be a value of x. What we don't know is the long leg, x square root of 3. If this is equal to 2x, let's solve for our x first. You've got 4 square roots of 3 is equal to 2x. What are we going to do? We're going to divide by 2. If you divide by 2 on both sides, this goes away. Rationalize this by doing the division, since that can be simplified. So that's going to be 2 square roots of 3. So if Mn is 2 square roots of 3, you've got 2 square roots of 3 times square root of 3, because we're just substituting this in for x, if that is my x, and then all we got to do is take this x and multiply it by square root of 3 to get my Ln. So again, you can only multiply what's underneath, but that's 2 times square root of 3 times square root of 3 is square root of 9, which is 3. So the answer would be 6. And that concludes Unit 7-4.